Hey guys, today I want to present a solution to the Canada Math Olympiad 28 problem 4. At first, let's have a look on the problem statement. We are asked to find all functions from the positive integers to the positive integers such that f of n to the power of p is congruent to n modulo f of p for all positive integers n and prime numbers p. Since we don't have any information about our f of p, it is hard to deal with this congruence here. Therefore, one first step is to plug in some value for n such that f of p divides one of these sides here. Therefore, one good idea is to plug in n equals p, which tells us that f of p to the power of p is congruent to p modulo f of p, but this tells us now that f of p must divide p. Here we can use the fact that p is a prime number and therefore has only two divisors, namely 1 and p, to conclude that f of p is in the set 1 or p. Let's consider the different cases for the values of f of p. And we start with the easiest case, namely that f of p is equal to 1 for every prime. We get that our congruence here now becomes f of n to the power of p is congruent to n modulo 1, but this is clearly true for every prime p and every positive integer n, and therefore for every composite n we can have f of n to be any positive integer. So we figured out our first solutions, namely all functions from the positive integers to the positive integers satisfying f of p equals 1 for all primes. Now we can go on with our second case, and in this case we now find a prime p such that f of p is equal to p. Plugging q into this congruence here for p, we get that f of n to the power of q is congruent to n modulo q. Here we can now make use of Fermat's-Lilje theorem, which tells us that this is congruent to f of n. This implies that q divides n minus f of n, and now since we have some information about the values f of p, it's a good idea to plug in p for n to get that q divides p minus f of p. This divisibility condition here is clearly true if f of p is equal to p, because then the right hand side is nothing but 0. Therefore, the only interesting case is if f of p is equal to 1. So let's have a look on this case. Here we can directly conclude that p is congruent to 1 modulo q. Since p is a prime number, it is not equal to 1, and therefore this congruence here directly implies that p is greater than q. So this case here is only possible for primes greater than q, and therefore we can conclude that f of p is equal to p for all p less than q. Therefore, it would be enough if we can always find a prime q1 which is not congruent to 1 modulo q and which is larger than q, because then we can argue that f of q1 is equal to q1, and therefore by the same argument as we made here, we get that f of p is equal to p for every prime less than q1. And then in the same way we can go on and find a prime q2 and so on to conclude in the end that f of p is equal to p for every prime number. But note that Dirichlet's theorem implies that for every non-zero residue class modulo q, we can find infinitely many primes in this residue class. In particular, there exist infinitely many primes congruent to 2 modulo q. But here we have to watch out, because if q is equal to 2, then this is congruent to 0 modulo q, and then we can't use Dirichlet's theorem. And therefore, we have to assume that q is not equal to 2. Let's have at first a look at this particular case where q equals 2 is the only prime number satisfying f of q is equal to q. Here, if we plug in a prime p greater than 2 into this congruence, we get a trivial congruence because we have a look at this congruence modulo 1, and therefore the only interesting value for p is 2, and then this congruence here tells us that f of n squared is congruent to n modulo 2. F of n squared is congruent to f of n modulo 2, and therefore for n composite we can choose f of n arbitrary in such a way that f of n and n have the same parity. So we are left with our last case in which we have that q is greater than 2. In this case we can make use of the argument I talked about before to conclude that f of p is equal to p for all primes p. Therefore our congruence becomes that f of n to the power of p is congruent to n modulo p, and now we can use again Fermat's little theorem to get that f of n to the power of p is congruent to f of n modulo p, and therefore we get that p divides f of n minus n. Let's choose p such that p is greater than the absolute value of the right hand side, and then this directly implies that the right hand side must be equal to 0. So we get that f of n is equal to n for all n in the positive integers. And this is our last solution, and then we are done.